All right, for this last example of using multiple regions, we are asked to find the area of the region bound by x equals y squared minus 3 and x equals 2y. And the first thing I would do is solve each of those for y. So the linear one is just y equals 1/2 x, but we have this quadratic. And so if I solve for y, if I add 3 to both sides, I get y squared equals x plus 3. And then when I take the square root, I need to remember to consider both the positive and the negative square root. So this becomes y equals positive square root of x plus 3 and y equals the negative square root of x plus 3. So hopefully we remember how to graph these from algebra. I graphed them already over here. So when we have x plus 3 inside of the square root function, that's going to translate this to the left 3. So this point right here is at negative 3. This top curve, so like we know what the square root function just looks like that. This top curve is our positive square root function. So this is the positive square root of x plus 3. The bottom curve is the negative root of x plus 3, and then this linear piece that goes through the origin is y equals 1/2 x. So when we're trying to find the area bound by, really it looks almost like 3 curves, I need to look at the 3 points of intersection. So I know there's one at negative 3, some other x value I don't know, and then some other x value that I don't know. So if I trace those, I get this region. All right, so at first it looks like a single region, and you might be wondering like, well, why is this in the multiple regions section? Well, let's look at what happens when we draw in our sample rectangles. If I draw a sample rectangle out here to the right, like on the right part of this curve, if I look at the top and the bottom, the top is the square root of x plus 3, and the bottom is that linear piece, the 1/2 x. But if I move to the left of this intersection, so like way to the leftmost side of this region, the top stays the same. So like my top function is still the square root of x plus 3. But the bottom function on this rectangle here is not the linear piece. Rather, on the left side of where 1/2 x and the negative root of x plus 3 intersect, the bottom is now the negative root of x plus 3. So in a few moments, we'll learn like an easier way to do this one. And in fact, instead of actually finding the area, let's just set up the integral so that we're not doing this example for the rest of our lives. All right, so we know generally that the area is going to be the integral from, if I start at the furthest to the left, I know that first x value is negative 3, but I don't know what this intersection is. So I'm going to come back to that. But for that piece of it, it's top minus bottom. The top is the positive square root of x plus 3. The bottom is the negative square root of x plus 3. So I still have to find that limit. And then we're going to add to it that same limit that I don't know from the last equations or the last integral. So starting right here. And then we're going to integrate all the way over until we get to the second intersection. So I don't know that value either, but we'll figure it out. And over here, the top is still the positive square root of x plus 3, but the bottom is 1/2 x. All right, so before we can say we're done, because we're not going to do the math unless you really want to, before we can say we're done, we've got to figure out where these two intersections are. So I'm going to go back to the original functions, and man, there's a couple ways to do this. We want the x values. Gosh, I'm trying to think. There's a few ways to do it. We could just set these original two functions equal to each other. So if I have x equals y squared minus 3 and x equals 2y, well, I know those x values are the same, so I'm looking for where y squared minus 3 is equal to 2y. And because this is a quadratic expression that also has a linear term, I'm going to subtract the linear term over and write this in standard form, set it equal to 0, and factor. This is not my first instinct the way I'm solving this, but I think it'll work out fine. All right, so when we factor, we're wondering like what multiplies to -3 and adds to -2. That's got to be a -3 and a +1. So we get that y is equal to -1 and +3 when we apply that zero product property. But we don't want to know what y is equal to, we want to know what x is equal to. So we could plug that into any of those original functions. I would use the linear one. So if x is 2y, I need both of those x values. So when y is equal to -1, 2 times -1 would give us a -2. So we have that ordered pair, -2, -1. And when y is equal to 3, x is 2 times 3, so 6. So we have that other ordered pair of 6, 3. And we actually don't really need those y values at all. So going back to the prompt, we said we're not actually going to work this one out for time because there's a lot of examples, I know. The next one's more important than this one anyways, they're the same problem. What we could do is we could write that our area is the definite integral from -3 to, we found that this has to be our -2. So from -3 to -2, top minus bottom is the positive square root of x plus 3 minus the negative square root. And that's the same as just adding these together. In fact, we could even just change that to multiplication if we wanted to. And then the second piece, from -2, we found out that this intersection happens when x is 6. So from -2 to 6, positive square root of x plus 3 minus 1/2 x. All right, we could evaluate that, but for time we'll stop.